All right, so I'm going to talk about friction now. Mostly, I'm just going to be summarizing the data that you got from the lab, and then we're going to talk about some of the main takeaways from the friction lab. First of all, I will note that we did not get a complete set of data. Unfortunately, just due to time constraints, we didn't get to look at everything, but I will fill in the blanks for you. Um, so I'm going to go to the summary here and just take a look. First of all, actually, let's look at the graph real quick. In each of these graphs, you see some sort of, there are definitely lines, and you can see that one line is steeper. In fact, the max force is steeper than the mean force, but they're both pretty much on lines, and that's really good to see. And each line you guys were asked to get the slope of, which is great. You guys typed that in, and this was happening for different amounts of things. Actually, Group 7, I think I had to change this. What did you guys do, Group 7? Do you remember which one you did? This looks like it might be plastic. Group 7, I think I had at the third table. You guys remember uh, which one you did? Cork, felt, plastic. I know it wasn't. I think it was felt. Okay, that sounds right. All right, felt. And this is, you guys did cork. That seems right. And then plastic. That looks good. Group 5 did plastic. That sounds right. Okay. Um, so here's the data that we collected. So we have one plastic, which you guys got similar data to. So we have 0.187 for the mean force and 0.173. That's pretty close. And then the max is 0.307 and zero point 0.2. That's not as close, but that's still pretty good. And then we have one cork here, which these are kind of close, although this one right here is pretty big compared to that one. And then we have only one group that did felt. And unfortunately, no one did two plastics, so we could not see whether or not surface area was a factor in this. But what I want to do is explain what these numbers mean and also explain what it means for the fact that these are linear relationships. There's a lot to pull out from this lab, so I'm going to do that all in some notes right here. So just as a recap, you guys were asked to do this lab, and you were pulling a cart with different masses in it, and you were pulling it with a hook. Uh, there's a force sensor that was plugged into the computer, and you were pulling it at constant velocity. And by doing that, you ensured that the applied force that was being measured by the force sensor was equal to the friction force that you're basically trying to measure. What you guys plotted was on the graph that I had there. You guys plotted normal force versus friction force, and that's what you were getting. Actually, I should make that black there so that I can make it different colors. Normal force versus friction force. And what you guys saw was two sets of data. You saw the mean looking something like that, and then you saw the average, or sorry, the max looking like that, and this was the mean, and this was the max. So I want to talk about that first, the mean and the max. So when you guys were taking data, and this was your time graph, and this was your force of friction, it looked something like this. You had data, it was increasing, you were increasing your force, increasing your force, increasing your force, and then suddenly, boom, it moved, and then you had this and this and this, and it looked like that. This was the mean, the max, I mean, and then this right here was the mean. This tells us that, excuse me, that there's two different types of friction. The first type of friction is called static friction, and we abbreviate that to be FFS, like that. And then there's kinetic friction. Static friction is the friction that you experience without it moving. It's basically the friction that you need to um, overcome before it moves. It begins to move. whereas kinetic friction is as it's moving, the friction that it experiences. So by looking at this graph, it tells us that, so all along here, the friction was matching the applied force. But then once the applied force became so great, whatever this force was right here, then once it started to move, the friction dropped to a steady whatever this is. So this right here is the kinetic friction, and this right here is the max static friction. It is possible for you to have a static friction between 0 and whatever the max is, right? So it could be 0, it could be 5, it could be 10, it could be, let's say 15 is the max, but then it drops, and then kinetic friction is somewhere always less than the max static friction. So that's number one. That's why we see two different lines. That's why we have two different types of friction. Number two, the other big takeaway from this is that there's a linear relationship between force and friction force and normal force. And if we write the equation for that, let me just scroll over here. If I make a y equals mx plus b equation for this, first of all, the y-intercept should be 0, so again, that goes away. And then I have force of friction on the y-axis, I have some slope, and then I have normal force on the x-axis. This right here is going to be our equation. The only question is, what does the slope represent? If I divide these things, friction divided by normal, I get some slope, but these are both newtons, right? So a newton's going to cancel out with a newton. So there's actually no units for this, whatever this slope is. It's unitless, which means that it's a ratio. Whoops, not a ration, a ratio. And what it actually is scrolling down, it's called the coefficient of friction. And it's just a ratio of the friction to the normal force. And it looks, and this is the variable for it. It's a Greek letter called mu. It looks like if we're back in first grade, and this is our, like, you make your A like this and stuff like that, it would look like this. All right. I have lots of students writing it wrong. They're like doing this and like all sorts of weird things. It like curves up from below, and then it goes like that. That's called mu, and it's a Greek letter. And so we can have two different mu's, right? This is going to tell us the mu of the max static friction, and then this is going to tell us the mu of the kinetic friction. And so that coefficient just tells us how frictiony something is. It usually is, so if it's 0, so it's usually greater than 0. If it is 0, then that just means that there's no friction. And it's usually smaller than 1. So if you get a coefficient of friction that's like 15, you did something wrong. Or like 100, you definitely did something wrong. It's usually between 0 and 1. It can be greater than 1. It's not impossible, but it's just usually between that amount. And it just tells you how frictiony something is. And so the equation that you get is this. The force of friction is equal to the coefficient of friction times the normal force. And this equation is on your equation sheet. But I want to show you what it looks like real quick. If I go to AP Physics 1 equation sheet, it looks super complicated on your equation sheet. Let me zoom in. It is right here, the 5th equation, and it's looking real funky there. So I want to show you what it is and why. So it basically is the absolute value of the force of friction is was it less than, or am I spacing on? Yeah, less than or equal to, is less than or equal to the coefficient times the absolute value of the normal force. So what this means is, the reason why it's an inequality is because, remember this part where it was going up, 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 and then down and did that, right? This is just saying that from here to here, it could be anywhere from 0 all the way up to the max static. So this, if you calculate it right here, that would be the max static if you put the coefficient of static friction there. And then we know that the friction would have to be either less than or equal to that. It couldn't be greater than it. And then if it's the kinetic friction, then it would just be as equal to coefficient of kinetic, and it would look like this. So, and the reason why they have the absolute values here is because the coefficient can't be negative, and so it's just going to be the magnitude of the force. So I usually just write it like this, but that's how it shows up on your equation sheet. So this is a big equation. It's on your equation sheet. You'll be able to calculate friction if you know the normal force. So that's pretty neat. The last couple things I want to just point out to you is that we had plastic, felt, cork, and then there was supposed to be 2 plastic. So these 3 were supposed to help us identify what happens if we have different surfaces. And what you should see is that different surfaces give us different coefficients. So I think the plastic ended up being around 0.2, the felt being around 0.3, and the cork was around 0.5 to 0.8. The truth is that they can be different depending on the surfaces, but if you just Google coefficient of friction, you can get a table of lots of different, let me say table. You can just find lots of different coefficients of friction. So rubber on dry concrete would be 1 for static friction. Steel on steel is 0.6 for static, or shoes on ice is 0.05 for kinetic. So that's why it's so low. That's why you slip really easily. So you guys can just look at that on your own time, but that's just an example of what's going on with that. And then the final thing is plastic. We're supposed to look at 2 plastic and basically see, does that equal, so if it's double the friction, then that would mean it should be 0.4, right? Because if plastic is 0.2, then doubling the plastic would make it 0.4. But actually, what you should have found out if you did do the lab is it would just be about 0.2, which means surface area actually has no effect on friction. So that sometimes comes as a surprise because we think more surface area means more friction, but it actually doesn't. So I tried to make this quick, but I think it took a little longer. But that's basically the basics of friction and what you should have gotten from the lab. I know we did it very quickly, but if you have any questions, I'll take them after I'm done canceling out of the recording. So thank you very much.